Hi everyone. So for this devlog, I wanted to show a bit of the work I've been doing for multiplayer. So if you look off on the horizon, you'll see a small dot making its way over here. That player is being controlled by a client on a laptop connected to my server on my home network. And from the perspective of the video, this is on a client on my desktop. And you'll see the client on my desktop has an animation running because it's running locally, but the networked character isn't just a simple T-pose. This is because I haven't really put in a lot of effort to have an animation system, especially one that works over the network. So there's not much more to show for the multiplayer, as right now it's pretty simple, just sending over the position and the orientation data. However, I'll go over sort of a high-level design and some of the sources I used for the first iteration of the network server. I've done some distributed system stuff in the past, but nothing with gaming, so I wanted to start my research with that in mind. So the first place I ended up was Gaffer on Games, reading these articles, and I thought they were really, really good, especially in laying sort of the foundation of some of the terms and ideas. I then started reading these articles about Quake 3, and I also started looking at the source code, which was super helpful. I then bought this book, which is the first volume of, I think, 9, and it was pretty good. It touched on quite a few topics and high-level ideas. So for the designs, I'm going to kind of keep them high-level and a bit hand-wavy. So for this first design, it's probably one that people have seen before in the past, or something very similar. This describes the interaction between the server and the clients. So over here, we've got an authoritative server that will periodically send snapshots, and I'll go over what that looks like. And the clients also send the client updates. So the client update basically has the player inputs along with the last snapshot that was acknowledged. This is for delta compression. That input basically is the key mappings. So for example, move forward is W, but it could be anything. Also the forward direction, which is currently being calculated on the client. And the snapshot itself basically has the current snapshot ID, the player ID, which is the player ID for that client, and then basically the world state in a map. So there's no interest management here. There's no optimizations. It's pretty simple currently. But now we can take a look at the server process, which is currently targeting Linux and running on Ubuntu. So on the left, we have the main loop, which has a tick rate of 60 ticks per second. So we'll call it 16 milliseconds. And within each tick, we want to check for network updates, which come across this channel. A channel is a one-way communication between threads. So the main loop, the network fiddler, and the state fiddler are all on their own thread. And I'm not doing this because of any sort of pre-optimization. It's more just to separate concerns and help organize things a bit. So for those who may have not worked with channels before, this is how I understand them. So let's say you have, I don't know, thread A and thread B. You could also have thread C because the channel can actually be cloned, at least for the receiving side. And let's say A has some data that it wants to share. And sorry for the handwriting. It's difficult to write on this thing. Okay. And B has its own memory here. And A wants to share 5 with B. And something like this via the channel, and then B can do whatever it wants. Now, if we compare this to how I've mostly in my career seen communication between threads, it's using something called shared memory. So let's say we have the same scenario, but down here, and it's not exactly like this always, but it's kind of a simple example. Let's say we have this, and A still wants to get 5 to B. So perhaps A needs to set 5 here, right? So A sets 5 here, and B needs to read 5, let's say, for this use case. And the problem is you need some layer around it that handles locking. And this comes with quite a nice array of bugs and data race conditions and things like this. And when you do end up with a bug, they're usually quite difficult to track down. So with channels, you don't end up with those same scenarios. However, the way that I'm using it, you do end up duplicating data, which I think is a decent trade-off. Some standard libraries and frameworks already provide data structures that can handle concurrent reads and writes. For example, in .NET, we have system.collections.concurrent, which has data structures that, are thread safe. But I've seen engineers in the past try to implement these types of data structures on their own and cause some issues down the road. So now that we understand what channels are in this context, you can see that this is checking for network updates, which is essentially emptying this channel, and it has a time allocation, of the tick rate minus t divided by 2. So the tick rate we said was about, let's say, 16 milliseconds in this case. And t is the time it takes to update and send snapshots. So updating a snapshot may be copying world state, whatever the case, and to send it to all the clients. So let's say t is a millisecond. So tick rate would be 16 milliseconds minus a millisecond divided by 2. So we're ending up with, what, 7.5 milliseconds of time for that tick to actually check for network updates. And the same goes for the state updates. It has the same time allocation. But it's very simple to change depending on what is taking more time, whether it's checking for state updates or network updates, whatever the case. So now if we look at the network fiddler, its job is really to listen for the UDP packets coming in from the clients and keep track of connections, and in the future, also disconnections. And it maps the clients to client IDs. So the clients will come in with a IP and port, and they will get assigned a client ID that will be used throughout the rest of the server. It'll also parse the client update from the UDP packet, and it'll send the network updates. And finally, we have the state fiddler, which will check for network events. It's really concerned with the client updates. It'll update the world simulation. So for example, if position changes or whatever the case, and then it will send state changes to the main loop. These again will be synchronized for the world state that lives in the main loop and the world state that is in the state fiddler. But the state fiddler is kind of the one source of truth as far as the simulation goes for the server. So finally, we can look at the client, which is running on Windows, and we have the game loop, and every frame, basically we're checking a channel for new snapshots. This is coming from another thread, which is listening for UDP packets from the server. It's parsing the snapshot and sending the snapshot. So this was quite simple. And then it wants to first create any entities that come in on the snapshot, so anything that didn't exist before, and then update the network components. So this would be updating the components that are networked, so the position and orientation of these components. Not everything is actually networked. And calculate the player look direction, update camera, render, and there's quite a few steps in between there that aren't really relevant for this talk. And then we send the client update to the server, which we saw on the other screen. So in the diagrams, I had shown sending and receiving data from the clients and server. And I know there's a lot of general solutions to that problem, but I kind of wanted to dive in a little bit deeper and show what I had done. So basically what I did was I created a library in Rust that the client and the server will use to serialize and deserialize types that library provides. And one thing I really like about Rust is, let's say I go to this serialize. Well, I can create a trait. So this is kind of like its version of polymorphism. So with this trait, I can actually implement it for types that are given by the standard library, which is really nice. And in here, I actually keep track of all the Indianness for the client and the server. In this case, I'm using little Indian. So now if we look at the public functions, so if we look, there's a few functions for serialization and deserialization. For serialization, we see this one has a previous snapshot, a current snapshot. This is for the delta serialization. Basically, it goes field by field, and if the values are different between the previous and the current for the field, it'll add a byte that's 1, and then it'll put the value. But if they're the same, then it'll just put a byte of 0. For deserialization, we need to deserialize the fields in the same order in which they were serialized. That's sort of the limitation to this simple design, but works in a similar fashion where it basically deserializes. Like, so for example, if we look at update field, if we look at deserialized field, it first checks if the byte is 0, then we just return nothing. Or if it's something, meaning the byte was 1, then we will actually attempt to deserialize the type. And this works out well because here, if it's sum, then it'll actually store the new value with the value that was deserialized. If not, it just takes the old value, which is coming from, in this case, the previous snapshot. So for deserialize, it's just the byte array that comes in from the UDP message and whatever the previous snapshot was. So on the client, whatever that snapshot was last received. You also have for the client updates, which these are also similar. And for these, I realized there are optimizations. For example, right now I'm serializing bytes, but this could be a bit field and it'd work just as well. But I wanted something that was quick and easy to do. So one final thing I'd like to talk about. In my last video, I mentioned using WSL2 for my development environment for the server, and it's worked out pretty well, except when I got to the networking part. And I ran into a few issues and some things that just aren't very pleasant that you can kind of work around. For example, the IP address changing on the virtual adapter. But there are some things like I couldn't get around, and they've linked a workaround here, but it's for TCP, and I'm using UDP. So instead of having to deal with that headache and really trying to kind of hack it to get it to work, I decided to switch to using the Ubuntu server that I built. This has worked out really, really well, and I can still kind of develop locally. At least it feels that way through Visual Studio, but it's compiling on the machine. And this has a benefit of when I'm actually debugging, I can debug different clients on the network instead of having to be on localhost for the most part. Anyways, thanks for watching the video. Take care.